Okay, guys, so let's get a little more practical. What do these absorption spectra look like, right? We've been talking about transition state dipoles. We've been talking about some of the quantum mechanical descriptions that give us the transition state dipole, right? And how central that is to this idea of absorption, electronic absorption of light by molecules we might care about. For example, molecules like the aromatic side chains of tryptophan, tyrosine, and phenylalanine, as I've pointed out, are so incredibly useful for quantitating the amount of proteins you have in a protein sample, right? So to make this a little bit more, little less abstract, let's take a look at an example, right? So here's a simple molecule, right? This is, of course, formaldehyde, simple carbonyl-containing molecule, one carbon, oxygen, carbon, oxygen double bond, a couple of protons, right? So if you think about that and you think back to some of your basic organic chemistry, you remember, of course, that carbon is 2 sp2 hybridized to the oxygen, right? So we've got these 2 sp2s bonding orbitals between the carbon and the hydrogens. We've got this 1 sigma bonding orbital between one of the other sp2 2 sp2 orbitals and a 2p x orbital in this orientation from the oxygen, right? And then above and below the plane of that sigma bonding orbital, we have the 2pz bonding orbitals with the carbon and the oxygen sharing electrons in this so-called pi bonding orbital, right? That gives us that carbon-oxygen double bond. At the same time, the oxygen also has electrons in these other lobes of these 2 px and py orbitals that are non-bonding, right? Okay, you guys hopefully remember all that stuff. Turns out that formaldehyde will absorb light, right? And when it does, it therefore has a transition state dipole that is coupled to a change in the electronic structure that I just outlined right here. That is a sort of the practical demonstration in some sense of what we were just talking about with the transition state dipole. So what does that mean when you have this absorption of light to the structure of electronic structure of a molecule like this, right? Okay, well, it turns out formaldehyde absorbs light somewhere in the range of about 300, say 360 nanometers, somewhere along in there, right? So it's ultraviolet light, absorption of ultraviolet light. And when it does, you get a change in the electronic structure. And this is written out schematically with an example kind of like this. Remember, here's that ground state that we talked about before. We've got the electrons in those pi bonding orbitals. Here are some electrons in the oxygen non-bonding orbitals. We absorb some light, we get a so-called pi to pi star transition, is where the easiest transition is going to happen from. So we get electrons in these pi orbitals will transition to an excited state, higher in energy, to absorb some of that light, with one of the electrons ending up in that so-called pi star orbital. So what does that mean in terms of the structure of the molecule? Well, the quantum mechanical calculations say it looks something like this. Here is looking down the x-axis. Here are the 2 lobes of that pi bonding orbital. And if you look down the y-axis, here's that sort of stretched lozenge, right, of the pi bonding orbital looking down the y-axis. The pi star orbital, the excited state, the sort of wave function sub 2 state of this molecule, looks different. If you look at down the x-axis, the pi star orbital, it looks similar, right? You got this positive lobe here and negative lobe here, basically looks the same. But look what happens when you now look down the y-axis. Instead of this nice extended sort of lozenge, you get this additional node that pops up in between, sort of splits. And each of those lobes now splits into sort of a positive and negative, positive and negative. So you get this sort of splitting pattern, right, in terms of the electron distributions, looking down the y-axis there, right? Okay, that's cool, because now if you do that spatial sum that we talked about, and you look at you applying that transition state or that dipole, electronic dipole operator, what you would find is the transition from this state, right, the pi state, to the pi star state here results in a redistribution of charge separation that has a particular orientation because of this spatial rearrangement that results in a dipole. And it has components laid out here by these little arrows in both the X, Y, and Z component, right? So this rearrangement of that structure into that pi star orbital has a particular spatial dimension, right? If you sum all of this up across X, Y, and Z relative to the molecular reference plane or the geometry of this molecule, right? Turns out you can also you can promote with even deeper UV light. You can kick electrons out of those non-bonding orbitals into that pi star. It's a so-called end pi star. Takes even more energetic photons of light to do that. Okay, so this isn't just like some sort of abstract thing for like formaldehyde. You can do a similar sort of thing, or the same thing applies to any organic chromophore, any absorbing bit of matter. Molecules, organic molecules, are going to have a behavior like this. They're going to have transition state dipoles that can be spatially mapped onto the reference frame or the geometry of that molecule. Here's an example, right? This is adenine, right? You guys may remember the UV absorption spectra of adenine, right? We've got a nice peak here around 260 nanometers where we all go measure our DNA concentrations. You may or may not know there's also a deeper ultraviolet absorption for the adenine nucleotide. And if you go through and you can either do the quantum mechanical calculation, there's the structure of adenine, or you can actually measure this. The transition state dipole for this 260 nanometer absorption lies in the molecular reference frame, sort of right across here, right? So it's oriented more or less across it's got a particular orientation relative to the carbons and the nitrogens and the hydrogens in this molecule, right? That's the rearrangement of that structure, right? The light is absorbed and the electrons in those pi bonding orbitals get kicked up into that excited state. The dipole that results has a particular orientation, right? And it's oriented that way across the molecule. Turns out this additional absorption down here has a transition state dipole as well, right? This deeper UV, this is kicking the molecule up into a higher excited state. So you'd have a system that essentially, you have a ground state, a first excited state, and then there's a higher level excited state. Why it takes more energy to get up there. And this one is oriented, in the case of adenine, it's sort of orthogonal, right, to the orientation, the dipole orientation, when you go from the ground state to that excited state, orthogonal to the one there at 260 nanometers, right? So like I said, this happens, like here's guanine, right? Similar sort of thing. You have sort of a nearer UV absorption down here. There's deeper UV down here, and the same kind of ideas. Those dipoles are oriented specifically within the molecular structure of these purine nucleotides, right? Okay, so a few more things, more practical things in terms of thinking about electronic absorption, right? Remember, right, sort of as an analogy to my particle in a one-dimensional box, these energy levels are quantized. And they're quantized because the wave functions that describe the ground state and excited state are eigenfunctions of this time invariant Hamiltonian, and then we can apply that time variable potential energy operator that pushes things around. But the states themselves, right, that the electronic structure that defines, say, the ground state or the excited state, it's time invariant. And because that's time invariant and satisfies, as we saw before, that time independent Schrodinger equation, the allowed energy levels are quantized. They're discrete. And transitions, electronic transitions, are only allowed between particular levels, which means the incident light coming in, right, has to match, its magnitude here has to match that energy separation, right, in some strict sense. Energy greater than or less than, right, that amount will not be absorbed. The light will simply pass right through undetected. So another way to think about this is that the magnitude of that transition state dipole has to match the energy separation or the light coming in has to match the energy separation of that transition state dipole, so that absorption only occurs between allowed energy levels. Okay. Another thing you'll note, though, the way this is drawn. So here, this would be sort of our ground state here. This is the ground. Yeah, so here's our first excited state. You'll notice that within that sort of, abstract manifold that describes those two states, there are all these other little subdivided, tiny little itsy bitsy little energy levels. Okay. So in electronic spectroscopy, each of those states, electronic states, has an associated set of rotational and vibrational energy levels. So those electrons, right, the nuclei, right, are sort of vibrating relative to each other, right? There are rotational energy levels of those different nuclei relative to each other. Those all have associated, discrete energy levels within that excited state singlet, right? So depending upon how those guys were oriented or where they are in an oscillation relative to each other, you have greater or lesser additional separations of energy, right? Okay. At the same time, let me get rid of all that stuff. It's important to remember that the separation, the fundamental separation between, for most of these vast majority of any organic molecule you'll ever come across, between the ground state and the excited state here is so large, typically, in excess, several hundred kilojoules per mole. These transitions can't be driven by thermal energy at room temperature alone. It's got to have that absorption of light. The energy separation is simply too large unless the chromophore absorbs light. Okay. One interesting question is, well, if these energy levels are discrete, why is it that electronic transitions, if we look back at what I showed you here for adenine and guanine, why are these things so broad, right? Why is it so big and loopy, sort of like this, right? And the reason for that is somewhat complex, but compared to, say, NMR spectroscopy or electron paramagnetic spectroscopy, which have very, very tight bandwidths to their absorption, there are a lot of other things that impact the sort of energy dispersion around each of those absorption events. There are Doppler effects, there's environmental heterogeneity. Doppler effects are a big one, right? That basically result in line broadening, right? So that you get an allowed transition across a wider distribution of energies than that simple tight diagram as the way we draw it would predict, right? Okay. So electronic absorption tends to have fairly broad spectra compared to other types of like NMR and whatnot. Okay, so what happens to that energy that was absorbed? We got to come forward, absorb some light. We push the system from a ground state to an excited state. Where's that energy go? Does it stay up there forever? Answer is no, right? That is an unstable separation of charge, right? The molecule wants to relax back to the ground state. There's a significant driving force for that molecule in that unstable excited state to get back to the ground state. For many, many, many molecules that absorb light like this, that transition back down here is a result of a release of heat, right? So the energy absorbed by the light that is contained in that rearrangement of the electronic structure of that molecule gets dissipated as heat as that molecule interacts with solvent and vibrates and all that kind of stuff. And the transition back down results in a loss of energy through heat of the surrounding medium, right? Okay, but there are a class of molecules that don't do this. They do something much more interesting, all right? For these molecules, which we refer to as fluorophores, that absorption of light, instead of being dissipated as heat, right, comes back out of the molecule through the emission of an additional photon, through the loss of energy and relaxation of the molecule from the excited state to the ground state by emission of light. And this is known, of course, as fluorescence, right? That emission is always going to come out lower in energy than the light that was absorbed, and that is a fantastically useful and important type of spectroscopy for learning all kinds of important things about biomolecules. Okay, now I mentioned before, this is just for calibration for timescales, I said that these electronic transitions, these absorption events are fast. Okay, well, what does fast mean? How fast is fast? Well, if you recall the Frank-Condon principle, that during this transition, the nuclei are basically frozen. Things happen so fast. Well, it turns out that absorption event, right, is basically, it's on the femtosecond time scale, right? In the range of a few femtoseconds, 10 to the minus 15 seconds, the absorption event happens, right? Then what often happens in electronic spectroscopy, a lot of these transitions happen up into instead of just the first excited state, there is a second or a third excited state. And these molecules will then relax back down into the lowest excited state through loss of heat in the process known as internal conversion. That happens on a picosecond time scale. Then the subsequent relaxation back down either through loss of heat or through fluorescence happens, it depends, right? These things can hang out up here for a nanosecond, 10 nanoseconds, 50 nanoseconds, something like that sometimes. And the subsequent event, actual transition event, again happens on the femtosecond time scale, right? Okay. So turns out there are a couple of other wrinkles to this. These first excited states that I'm referring to here are sometimes referred to as singlets. You guys remember, hopefully, that electrons in molecular orbitals like this are paired in such a way that one of their fundamental quantum numbers, their spin number, are opposite each other, right? That's an important property of electrons in molecular orbitals like this. And that's usually how things are going to stay. For normal absorption and for fluorescence, the molecule that gets driven from the ground state into an excited state retains a spin that's opposite to its partner that was left behind, right, in the ground state. Okay, but there are situations where that electron in an excited state can flip its spin. You see this guy now has the same spin as the electron that was left behind, right? This is a process that's known as intersystem crossing, right? Can happen on the sort of nanosecond or so time scale. And this generates something known as a triplet state. And triplet states are really interesting because they can be super long-lived. These things can live for milliseconds or even seconds in some cases. And they will subsequently decay, often with emission of light through a process that's known as phosphorescence, right? And phosphorescence, in addition to just being kind of a cool phenomenon when you look at little glow sticks and stuff, can be useful for doing all kinds of interesting science on biomolecular systems at much longer timescales, right? It's also a really, really useful tool. Okay. And with that, I think we're going to stop our discussion about sort of the basics of light absorption by matter and some of the quantum mechanics and then some of the practical aspects of it. And we're now going to turn in the next lecture to assuming that we can use tools like this to start studying some basic properties of molecular systems, right?